Greetings everyone, this is Professor Roman. Let's continue the group theory lectures. We've been talking about cyclic groups, and if you recall from an earlier lecture, I had said that cyclic groups are among the simplest groups, and yet there are some aspects of cyclicity that are not so simple. And I mentioned that it is possible to show that the groups Zn star are cyclic if and only if n is equal to 2, 4, p to the e, or 2p to the e, where p is an odd prime. And I believe I mentioned that that was not at all easy to prove, and that we would not prove that result, but we would prove later in the course that Zp star is cyclic where p is a prime. Well, I changed my mind. We are going to prove that Zp star is cyclic for p prime, and then we are going to prove the general result. Now this is going to be a bit heavy going, and strictly speaking, the proofs we're going to give are not really that critical to future study. So if you decide, if you want to skip this lecture, you can without prejudice, or if you get partway through and it's just too much, you're getting bogged down, you can skip the rest of it. So here we go. We're going to first prove that Zp star is cyclic for p prime. And actually, once we have established that some well-known properties of real polynomials also hold for polynomials over any field, then the proof that Zp star is cyclic for p prime is going to be actually quite simple. So we need to start by looking at fields. The real numbers R form the prototypical field because R is an abelian group under addition. The set R star of non-zero real numbers is an abelian group under multiplication. So we have two abelian groups here, one additive and one multiplicative, and the distributive law holds, and that connects the two binary operations, addition and multiplication. Well, this is in fact the definition of a field with one additional requirement. A field must contain at least two elements, and this is a technical requirement that's just to avoid some technical issues. An equivalent way of saying that a field has to have two elements, as it turns out, is to say that the additive and multiplicative identities must be different. So in symbols, 0 is not equal to 1. It's certainly not an unreasonable assumption or requirement. So here's the official definition of a field. A field is a non-empty set F together with at least that has two elements, together with the following properties. F is an abelian group under addition. F star, the set of non-zero elements of F, is an abelian group under multiplication, and the distributive laws hold. Of course, the familiar number systems, Q, the rationals, R, and C, are infinite fields under the usual operations, but the integers do not form a field. The set of all rational functions over R, something you probably studied in calculus or analytic geometry when you tried to graph these rational functions and find their asymptotes and so on. These form a field under the usual operations as well. There are also finite fields, as I discussed much earlier in the course. The finite field that's of interest to us here is Zp, where p is prime, because we're trying to show Zp star is in fact a cyclic group. We have seen that ZP is an abelian group under addition, and we've also seen that ZP star is an abelian group under multiplication, and I'll leave the distributive law for you. So ZP is a field when P is prime. Fields are, well, very nicely behaved in many respects because their properties are quite restrictive, but not so nicely behaved in other respects. If you remember when we talked about widgets, I talked about the Cartesian product. The Cartesian product of groups can be made a group, and same for rings, but it doesn't work for fields. We talked about quotient widgets. I said there are quotient groups, quotient rings, but there are no quotient fields. It's the asymmetry between addition and multiplication, the fact that 0 doesn't have a multiplicative inverse that somehow underlies some of this different behavior than you find in groups and rings. One of the nice features of fields is that they do not contain 0 divisors. A non-zero element A in a ring R is called a 0 divisor if there's a non-zero element B in the ring for which either AB equals 0 or BA equals 0. You wouldn't need both of these if the ring was commutative, but we don't know that, so either one of these is sufficient. The presence of 0 divisors can cause some rather unpleasant behavior in rings. In fact, it's well known to students of elementary linear algebra, in fact, that the ring of n by n real matrices has 0 divisors, at least for n bigger than or equal to 2. So here's an example. The product of these two non-zero matrices is the 0 matrix. So these are 0 divisors. Okay. In a field, every non-zero element has a multiplicative inverse, and so you cannot have 0 divisors. If the product jk is equal to 0 and k is not 0, then we just multiply both sides of this by k inverse, and we get j equals 0. So you can't have two non-zero elements of a field have their product equal to 0. No 0 divisors. Well, if n is not prime, then Zn will have 0 divisors. Because if n is equal to j times k, where j and k are bigger than or equal to 2, because n is not prime, it factors non-trivially, then in Zn, the product jk is equal to 0, because it's 0 mod n. So we have 0 divisors. So this shows that Zn is a field if and only if n is prime. And that's quite an important result. Okay. Now we need to look at polynomials over arbitrary fields. You've undoubtedly spent considerable effort studying polynomials over the real field, and much of the properties that you've learned for real polynomials actually applies to polynomials over any field, including ZP, primarily because there are no 0 divisors. So, for example, for polynomials over the real numbers, we have the usual degree formula. The degree of the product is the sum of the degrees. This property is a consequence only of the fact that the real field has no 0 divisors, so it holds for polynomials over any field. On the other hand, if the base is not a field, but only a ring, things are different. For example, for polynomials over Z4, if you take the product of these two polynomials, this degree 2, degree 1, if you look at the leading term, you'll get 4x cubed, but 4 is equal to 0 in Z4. You have to take the residue mod 4. So the cubic term disappears, and you have a quadratic here. So degree 2, degree 1, but the product is only degree 2. And the degree formula fails. Now, it's well known that a real number alpha is a root of a real polynomial, p of x, if and only if x minus alpha is a factor of p of x. Extremely useful fact when studying real polynomials. But this also holds for polynomials over any field. First of all, if x minus alpha is a factor of p of x, then you can factor like this. When you plug in x equals alpha, you get p of alpha is 0 times q of alpha, which is 0. Okay. So alpha is a root of p of x. Conversely, if p of alpha is 0, and let's say p of x looks like this, where a(n) is not 0, so it has degree n, then plugging in again alpha, we get 0 equals p of alpha is this expression, and we subtract these two. P of x then looks like this, but each of these is divisible by x minus alpha, and so p of x is divisible by x minus alpha. And q of x has degree n minus 1. So alpha is then a root of p of x if and only if x minus alpha is a factor of p of x. Now we can prove that any polynomial p of x of degree n over an arbitrary field f has at most n roots. And we can do that by induction. For n equals 1, we have a linear polynomial. A is not 0, and the only root of this, of course, is negative b a inverse. So we can then assume the result is true for all polynomials of degree less than n, and suppose that p of x has degree n. If p of x has no roots at all, then of course it has fewer than n roots, less than, at most n roots. Otherwise, if alpha is a root of p of x, then we can factor like this. And since q of x has degree n minus 1, less than n, the inductive hypothesis implies that q of x has at most n minus 1 roots. Finally, a root beta of p of x then satisfies this equation. 0 equals p of beta equals beta minus alpha q of beta. And this is the key point, since f has no 0 divisors, one of these two at least has to be 0. So either beta equals alpha, or beta is one of the at most n minus 1 roots of q of x. So p of x has at most n roots. So those two facts, the roots relate to factors, linear factors, and polynomial of degree n has at most n roots, apply not just to polynomials over the reals, but to polynomials over any field. Now we can prove a very important result in the theory of finite fields. And it's one that shows that ZP star is indeed cyclic. if f is a finite field, then the multiplicative abelian group f star of all non-zero elements of f is cyclic. So, as to proof, suppose that the size of f is n. N is a finite f is a finite field. Since f star is abelian, it's an abelian group, we had a theorem in chapter 2 that told us that the order of every element of f star divides the maximum element order. We did a proof by contradiction. If we assumed that if a root didn't have order dividing the maximum order, if we assume that, then we could produce an element that had order bigger than the maximum order, if you recall that proof. So we denote the maximum element order by m. Every element order divides m. That means that every one of the n minus 1 elements in f star satisfies this equation. You raise it to the mth power. M is an exponent then of every element in f star, so you get 1. Or put another way, the n minus 1 elements of f star are roots of this polynomial. But this polynomial has at most m roots. That's why we went through the previous discussion, so we could say that. So Lagrange's theorem tells us that n minus 1 is less than or equal to m, and this is where Lagrange's theorem says m divides the order of the group. The order of an element divides the order of the group, but this order is n minus 1. So the only way to deal with this is that m equals n minus 1, which is the order of f star, which means that the maximum element order, m, is in fact equal to the order of the group. So whatever element has that maximum order generates the whole group, and the group is cyclic. Well, since ZP is a finite field, ZP star is cyclic. Okay. So this came out with no effort whatsoever once we established some relatively basic facts about fields, and especially finite fields. And there is a moral here to this discussion, and that is that all branches of algebra, and actually in all branches of mathematics itself, are strongly interconnected. It would be virtually impossible to study group theory, for example, without some knowledge of the other branches of algebra, such as ring theory, field theory, lattice theory. All these branches of algebra are kind of intermixed a little bit, and you can't isolate any of them without studying any of the others. Okay, now we know that ZP star is cyclic. Let's move on. As I mentioned at the beginning of this video, I said earlier that Zn star is cyclic if and only if n is 2 for p to the e or 2p to the e, where p is an odd prime. So to prove this, we will begin with a necessary lemma. And it doesn't look like it has anything to do with the matter at hand, but you will see later that in fact we need it. Let p be a prime and let d be bigger than or equal to 1. Let m sub p of n denote the largest exponent e for which p to the e divides n. Then for any k between 1 and p to the d, mp of this binomial coefficient p to the d choose k is equal to d minus mp of k. So in words, the largest exponent, e, for which p to the e divides this binomial coefficient is equal to d minus the largest exponent, let's call that e, of p that for which p to the e divides k. Okay, so let's look at the proof. The binomial coefficient p to the d choose k is equal to this when you write it all out. And if u lies between 1 and k minus 1, then for any I in the range from 1 to d, p to the I will divide u if and only if it divides p to the d minus u. Because I is in this range, p to the I does divide p to the d. So p to the I, a power of p, will divide the denominator if and only if it divides the numerator. And that applies to all of these fractions here, excluding the first one. Everything inside the square brackets. So we can go through these one at a time and cast out the largest power of p that divides the numerator, and therefore it will divide the denominator. We'll cancel them both. That means that this binomial coefficient can be written in this form, p to the d over k, that's this first factor here, times an expression of the form alpha over beta, where p does not divide alpha and p does not divide beta, because we've cast out all the powers of p in all of these quotients. Well, now when we look at this, we can see more clearly what mp of this binomial coefficient is. So in words again, it's the largest exponent e for which p to the e divides this. So that's equal to the largest exponent e for which p to the e divides this. But alpha and beta have nothing to do with p. They're not divisible by p. So in fact, this is equal to the largest exponent e for which p to the e divides p to the d over k. And that's going to be, if k was 1, for example, that would simply be e equals d. That would be the largest power of p that divides p to the d. But because k may be divisible by p, we have to take out the largest power of p that divides k. So we subtract that exponent from d, and we get this. Okay, that takes care of the lemma. Now, let's see, rather than tackling Zn star directly, let's try, we've taken care of Zp star, let's see what we can do with Zp to the e star. So prime power, a power of this prime here. Okay. We want to determine which of these groups is cyclic. Well, if e equals 1, then it's Zp star, and we've already seen that cyclic because Zp is a finite field. So we can assume e is bigger than 1. And this is the order of this group, Zp to the e star. So let's start with, I suppose, what is arguably the simpler case, and that's p equals 2. it's pretty easy to see that Z2 star and Z4 star are cyclic. You can just show that directly. So that dispatches the case E equals 1 and E equals 2. So we can now assume E is bigger than or equal to 3. Now the elements of Z 2 to the E star are actually odd integers because by definition this group consists of the integers from 1 to 2 to the E minus 1 that are relatively prime to 2 to the E, which means they are not divisible by 2, so they're odd. So an arbitrary element of Z 2 to the E star will have this form, 1 plus 2a, and it's not difficult to show by induction that 1 plus 2a to the power 2 to the k can be written in this form, 1 plus 2 to the k plus 2 times something else, some other integer, x sub k. And this is valid for k bigger than or equal to 1. Let's look at the case when k is 1. This side is 1 plus 2a squared, which is 1 plus 4a plus 4a squared, which can be written this way. Now what we need is 2 cubed, because k is 1. But we have it because 1 of a or a plus 1 must be even. So we can yank out a 2 from whichever factor is even and get 1 plus 2 cubed x sub k. And if we assume the result is true for k, that this computation will handle the case k plus 1. What we do is we pull out an exponent of 2 here so that now we can apply the inductive hypothesis to this, turns it into this, multiply it out, gather it this way, and there's your 2 to the k plus 3, which is 2 bigger than this exponent here, k plus 1. So you can check that for yourself. But actually, the basis step is a tiny bit trickier than the other steps. Okay, so we have established this relationship. Now, remember that we're trying to show that, well, actually, what we are trying to show is that we're trying to determine whether Z2 to the E star is cyclic or not. E is bigger than or equal to 3. The order of this group is 2 to the E minus 1. This has to be fixed. That should be phi of Z2 to the E star. Okay, so if we set k equal to E minus 2 in this formula, then 1 plus 2 to the 2a, which is an arbitrary element of the group, raised to this power 2 to the E minus 2, is equal to 1 plus 2 to the E and something else, x sub E minus 2. This is congruent to 1 mod 2 to the E. Or as elements of this group, Z2 to the E star, what this is saying is that if you take an arbitrary element 1 plus 2a in this group and you raise it to this power, you get the identity. Because in here you do everything mod 2 to the E. So 2 to the E minus 2 annihilates every element of the group, but the group has order. This is where I have to fix this. 2 to the e minus 1. So no element of the group has order equal to the order of the group, which means the group can't be cyclic. It has no generator. So what we have learned from here up to here is that for the case p equals 2, the even prime, z2 star and z4 star are cyclic, but none of the other zp to the e stars are cyclic. So I'm going to just jump ahead to the theorem that summarizes what we're doing, and we have quite a ways to go yet. And I just want to point out that we have just established that zp to the e star is cyclic if and only if this is the odd case for p odd, but from p is even, p to the e has to be either 2 or 4. So we've dispatched this second case here. Now we need to work on this one, which says that zp to the e star is cyclic for any odd prime. And any exponent e bigger than or equal to 1. So that's where we are here. Now assume that p is greater than 2. So in other words, p is odd. To show that zp to the e star is cyclic for all odd primes and for all e bigger than or equal to 1, it would be sufficient to find elements of the group that have these two orders, two elements, one of order p minus 1, one of order p to the e minus 1, because these two integers are relatively prime. So if we find an element of order p minus 1 and an element of order p to the e minus 1, because the group's abelian, the product of those two elements will have order p to the e minus 1 times p minus 1, which is the order of the group. And we'll know that the group is cyclic because it has an element of order equal to the order of the group. So we've got two tasks ahead of us. First, we need an element of order p minus 1 in this group. Well, here is one way to find such an element. Let A be a generator of the cyclic group ZP star. We know ZP star is cyclic. Okay. So the order of A in ZP star is p minus 1. That's kind of a step forward. The problem we have is that ZP is not a subgroup of ZP star is not a subgroup of ZP to the E star. It is a subset, but it's not a subgroup because the binary relations are different. In ZP star, we multiply mod p. In zp to the e star, we multiply mod p to the e. Nonetheless, because zp star is a subset of zp to the e star, in other words, because a lies between 1 and p minus 1, it also belongs to the bigger group. So it will have some order in the bigger group, and this is the order of the bigger group. So A will have, as an element of the bigger group, let's refer to, it's easier if I say ZP star is the smaller group, ZP to the E star is the bigger group. Okay. This is the order of the bigger group, so the order of A as an element of the bigger group has the form some power p to the k, some power of p, k is less than or equal to e minus 1, and m divides p minus 1. So this is the order, this must be the order of A as an element of the bigger group. M divides p minus 1. Okay, then this is another way to say what I just said. P to the k m is the order of A in the bigger group, so A to the p to the k m is this is actually congruent. Equal is okay too, but usually congruent is a more appropriate symbol. Congruent to 1 mod the order of the group. And E, well, actually, I guess we're at E bigger than or equal to 1. I'm sorry, E bigger than or equal to 1. But we dispatched the case E equals 1, so we have to deal with the case E greater than 1. Okay? And because E is greater than 1, P to the E minus 1 is divisible by P. So what this says is that this minus 1 is divisible by this, and therefore this minus 1 is divisible by P, which looks like this. Okay. So what this tells us is that A to the P to the K M is congruent, again, congruent to 1 mod P, so P to the K M is an exponent of A as an element of the smaller group, because we're doing mod P now. And so P minus 1, which is the order of the element as it lies in the smaller group, divides P to the K M. So what we've actually learned here is that A has two presents. It's two universes. It belongs to the smaller group, it belongs to the bigger group. This is the order of A in the smaller group, this is the order of A in the bigger group. What we've learned is that this order divides this order. But P minus 1 and P to the K are relatively prime. And so P minus 1 divides M. But we just saw earlier that M divides P minus 1, so M has to equal P minus 1. So in the bigger group, A has order P to the K M, which is now P to the K P minus 1. Therefore, if we raise A to the power P to the K, the order of that element, A to the P to the K, is P minus 1. And that's what we were looking for. Again, this is because these two factors are relatively prime. So that's one of our tasks. Now the other task is to find an element of order P to the E minus 1 in this bigger group. We no longer need the smaller group. So this is Z P to the E star. Okay, now this is where we're going to use that lemma about binomial coefficients, because what we're going to do is take 1 plus p and raise it to the p to the nth power, where n is any number between 1 and e minus 1. Binomial formula, pull out the first two terms. We're assuming now that e is bigger than 1. Let me just jot that over here, because as I said, I hope I said it clearly, as far as z p to the e star is concerned, when e is 1, it's z p star, and we already know that's cyclic. Okay. All right, now, the lemma that we started this discussion with tells us something about these terms, the terms in this sum. This is why I pulled these two out. It tells us that the largest exponent e, for which p to the e divides p to the n, choose k, is n minus mp of k. But I am interested in the largest exponent of p for which p to the e divides the entire term here. So that's this number. And that should be equal to this number plus k, because I have p to the k here. So it's n plus k minus mp of k. Now, k minus mp of k is, in words, k minus the largest exponent of p that divides k. So let's say that's p to the e. Let's say e is that largest exponent. Okay, so p to the e divides k. Now when you take k and subtract e, k has got to be considerably larger than e. Even if p was 2, well, we know p is at least 3. You're looking at 3 to the e divides k. How is e going to compare to k? Considerably smaller. Small enough so that this number is bigger than 1. Okay? Bigger than or equal to 2 at least. Okay? Now, we can write this expression. See, the point here now is that p to the, maybe I should have written this as greater than or equal to n plus 2, because p to the n plus 2 will divide each of these terms. Maybe a higher power of p, but I don't care. P to the n plus 2 at least. This is divisible exactly by p to the n plus 1. So what I can do is write this here, keep the 1, factor out p to the n minus n plus 1. This will be a 1, and each of these terms will still be divisible by p. So this will be 1 plus p times something. And I called that w because all I care about is that p does not divide w. It will divide all the other terms, but it doesn't divide this term, which is 1, once I pull out p to the n plus 1. Okay. So that's where we stand now. So if I set n to e minus 2, I have 1 plus p to the power p to the e minus 2, and that is 1 plus wp. This is 1 bigger than that n there, so this will be e minus 1. P does not divide w, so p to the e does not divide this expression. Well, no, I shouldn't have said that. I should say this is not congruent to 1 mod p to the e. If you subtract 1, p to the e does not divide this. Okay, that's what I meant to say. Okay, So 1 plus wp to the e minus 1 is not congruent to 1 mod p to the e, because p does not divide w. So p to the e does not divide this. But if I kick up the exponent one more, 1 plus p raised to the p to the e minus 1, that is equal to this. Now this is congruent to 1 mod p to the e. So these two say that in the group z sub p to the e star, 1 plus p is not annihilated by p to the e minus 2, but it is annihilated by p to the e minus 1. So the order of this element is p to the e minus 1, which is what we were looking for. Phew, that's, you know, each step is not that difficult. It's some slightly unpleasant algebra. But this isn't deep mathematics, it's just complex. You know, to think of all of this was not so easy. But that verifies this first part of the theorem. So we now know that the group z to the p to the e star is cyclic if and only if p is odd, in which case e can be anything greater than or equal to 1, or p is even and e is 1, or e is 2. So you get p to the e is 2 or 4. And we have the complete story on z p to the e star and its cyclicity. Now we're ready to tackle the full theorem. And here's what it's going to be. If n can be written as a product of prime powers, where the primes are distinct, the exponents are bigger than or equal to 1, then Zn star is isomorphic to this external direct product. And moreover, Zn star here is cyclic if and only if n is one of the numbers we've been talking about, or p is an odd prime. Okay, so what about the proof? Well, for convenience, let's write pi to the ei as just ri. For this isomorphism, we need a map from Zn star to this external direct product defined by sigma sends u to u mod r1 through u mod rm. And I'll leave it for you to check this is actually a group homomorphism. It follows from the nice properties of residue class, taking residue classes, modular arithmetic. As to the kernel, suppose that sigma u is the identity in the external direct product. Then u is congruent to 1 mod ri for all I from 1 to m. We have a system of congruences where the moduli r sub I are pairwise relatively prime. So we think of the Chinese remainder theorem. It tells us that there's a unique solution to this system of congruences modulo the product of the ri's, that's equal to n. So there's a unique solution mod n. Or in other words, there's a unique solution in Zn star. Well, u equals 1 is such a solution. Okay. So it's the only solution. In other words, the kernel of sigma is trivial. The only u that fits this is u equals 1. And so sigma is injective. Moreover, the domain and the codomain of sigma have the same size, finite size, and so that means sigma is also surjective. Injectivity implies surjectivity in that case, and so sigma is an isomorphism. And that gives us the first part here of the theorem. Now, an earlier theorem, 7.9, from the last lecture, will imply that Zn star is cyclic. Let me bring this back again. That Zn star, where'd it go? There we go. Zn star is cyclic if and only if each of these is cyclic and their orders are pairwise relatively prime. Well, we already know that each of those is cyclic. We already know when each of those is cyclic from this theorem. Okay? So that theorem tells us that Zn star is cyclic if and only if pi is odd, or pi to the ei is 2, or pi to the ei is 4. That takes care of the cyclicity of these individual factors, and these orders are pairwise relatively prime. Okay. Well, let's take a look at the parity of these orders. There are three possibilities. If pi is odd, then the order of this particular group, which is this, is even, because pi is odd, pi minus 1 is even. If pi to the ei is 2, then the order of the group is 1, which is odd. And if pi to the ei is 4, the order of the group is 2, which is even. So, under what circumstances can we have a direct sum that looks like this without violating the pairwise relative primeness of the orders of the factors? Okay, so to have pairwise relatively prime orders, we cannot have more than one group from any one of these. If you have two of these, you've got two that are even, two orders that are even, and so they're not relatively prime. If you have two of these or two of these, you will not have pairwise relatively prime orders. So you can have at most one from each of these, but you cannot have one from door 1 and one from door 3, because those are both even. Okay, so at most one from each of these, but not from both 1 and 3 at the same time. And that leaves you with this Zn star can be Z star. If you just have one factor in your direct sum decomposition, then Zn star could be Zp to the E star, that would be the first one, or Zn star would be Z2 star, or Zn star would be Z4 star. If you're going to have more than one, it has to be excuse me, it has to be an odd and an even. Okay. So you can have Zn star is from number 2 and from number 1. 1, And this has order 2 to the p to the e. So I've got 2 to the p to the e, I've got p to the e, I've got 2, and I've got 4. And that's it. So there you are. That's the proof, and I told you it was not easy.